get started. Welcome to my talk. My name is Philipp Haller, and the topic will be asynchronous streams in direct style with and without macros. And some of these words will only make sense later on in the talk. So just a couple of words about myself. I'm a faculty member at KTH, Royal Institute of Technology in Stockholm. And before joining KTH, I worked at TypeSafe, which is now called Lightbend, which is essentially a startup that develops and maintains the Scala programming language, the current stable releases. And I've done a lot of work on concurrent programming in Scala, so I worked on actors, futures, async support, and join patterns, and others, and I also contributed to Akka. And so I'd like to introduce today's topic with a simple task. So the idea is that we're given an asynchronous method, a day of year, that returns the day of the year as a string wrapped in a future. So who of you has used futures before? Most people. Very good. So that's a good starting point here. So here are some examples. So if the current day of the year is April 11, it's going to return, for example, 04/11, but, well, wrapped in a future. So asynchronously we get that result. And but this method could also complete its future with an empty string or null or something else even. And so our task is now to create a future that is completed either with a string it's month so-and-so, where month is textual representation, so like it's April, let's say, right? Or it returns a default string if we can't really, if the string in the future doesn't match our pattern here. Okay, so now let's try to create a solution for this problem. And who of you likes functional programming? Okay, so carry on. There's at least half the people like functional programming. That's good. So that then should be easy to make a solution, right? Where we're just using futures and higher order functions like flat map and map, right? Where we say, well, let's call day of year. That returns a future, and we have higher order functions defined on it. And here we use, flat map and pass a closure, yada, yada, yada. Actually, to explain this, I think we need to I'm just want to break it down in a couple of steps so that we can all understand the solution. So here, actually, I'm calling a method that, given an integer, also returns a future with a string. So I want to simulate a situation where we're calling lots of methods returning futures, and that's the case, for example, if you use microservices or whatnot, like in Twitter's Finagle framework, there's lots of futures floating around, right? So that it's quite realistic that we're calling methods returning futures all the time. So okay, so this guy returns future of string. Now I want to transform that future into another future of string, but where the name of the month is transformed into this kind of string that we would like to have, right? So that thing also, of course, evaluates to a future of string, and as soon as the future returned by name of month is completed with April, the result of map is a future that's completed with it's April, right? Fine. So we do this. We see that this whole expression here we're just matching a string. I hope people are not tripped up with Scala syntax. I'm actually trying to use very minimal Scala syntax in this talk, but it's really just matching the string against, in this case, a regular expression. But Scala has very nice support for regular expressions, by the way. So if you haven't used that, you should look into this. But we're just matching against a regex, and we can extract month and day and so on. But this whole thing, of course, evaluates to a future of string. Great. Now let's get to flat map, right? And flat map, well, what does it do? This takes a bit more to explain, right? So essentially, flat map returns a future, let's call it f. And second, how do we complete f? Well, once day of year completes with a value, day string, we run our closure here, the whole closure. That results in a future, call it g. And when g completes with a value v, we complete f with v. Right? So we do this kind of future pipelining. Now, if you look at this kind of solution, we need this huge bubble to explain what's happening, right? So clearly there must be a way to make this a little nicer. So this is where a project comes in. It's called scala-async that I developed together with Jason Zaug from Lightbend, which aims to simplify programming with futures so that we don't need to use a lot of higher order combinators and so on. And this is available for current Scala versions. And so let's try to use that one. And here our solution looks a bit different. So first of all, we create this async block, and an async block essentially returns it creates a future. And the value that the future is completed with is simply computed as the result of the body of the async, right? So fine. So all we need to do is fill in the code that should compute the result of our future. What do we need to do? Well, we need, of course, the result of the future returned by day of year. And now it's possible that the result is either already available or it isn't, and we still have to wait for it. And so here we can use this method await and pass it a future. And what await does is it checks if the future is already completed, in which case we can take the result and just continue our execution with that result. Like we directly have the string, can match on it, etc. Or if that future is not completed yet, well, we actually suspend the enclosing async block, and as soon as the future is completed, sometime later, we will resume that computation. And by the way, we will not do this by suspending the underlying thread of execution, okay? Instead, when await needs to suspend, we actually free up the underlying thread that's running this code, so that thread, which is typically a worker thread in a thread pool, so that thread can actually continue executing other tasks. Right, so it's actually a very concurrency-friendly operation, this await, right? And so, okay, so we can just essentially call await, and well, the next piece of code we can just continue writing as if we already had our result, right? And so we can the result of await, we just match on it, etc. And then down here we call name of month, which returns a future. So clearly we need to await its result so that we can continue onward, right? And so if you look at it, this is actually quite a simple sequential program, right? Like first do this, then wait for that result, then do that. So it's sort of much simpler to explain, right? And so that was sort of the goal of this project. And of course, this model has been realized in many languages, also C# and other languages. Now, of course, if you look at this, you also, and you know Scala, you could say, wait a minute, actually Scala has what's called for-comprehensions, which is akin to Haskell's do notation, right, or like a general form of kind of sequence comprehensions, right? So we could also use those, right? So that would clearly, the program would look somewhat similar, because we can make this for-comprehension where we say, well, we have generators. And now the thing is that on the right-hand side of this arrow, we actually have expressions evaluating to futures. And so what happens is, like the for comprehension actually desugars to invocations of flat map and map. So this code is actually equivalent to the code I showed you earlier, right? But it's a bit nicer to write, because we can just write our future expressions. This is their results. Once they're completed, and so on, right? So we can again write essentially this kind of sequential code. Down here, we even have a nested for expression, right? Because we're actually producing a future based on the result of name of month, which is a future. And in the default case here, we can actually just create a future that's already completed with the default string. Right, so this is sort of an alternative way. Now, readability, I would say, is okay, not great, right? Like it's sort of, and we can make this very concrete because if you compare with the solution, first of all, here, we don't have to name all the intermediate results, right? And like we all know that naming is hard. It's difficult to come with good names. So if you're forced to come up with names all the time, that's actually can be bad, right? Especially if it doesn't help readability. Like here, for example, we're forced to come up with this day string variable name, right? Which is not super exciting, right? And then the response is like a super general name, and then we were forced to come up with this name variable. I mean, these are not really helping readability. So yeah, I would say it's not good if you're forced to come up with names all the time. Also, here, we don't have this explicit future successful invocation, right? So, and I would say this is actually kind of a low level, it's almost like an implementation detail, right? That we're like constructing a completed future, you know, this is sort of, it leaks through that we have this kind of flat map operation, and it's nice if you don't have to do that. And because so why is that? Well, we don't want to think about what the desugaring looks like, right? No, we want to write on a higher level and not need to know what the compiler spits out as the code, right? Then also what's interesting is that this solution actually can be more efficient too. So, and the reason is that one async block corresponds to exactly one closure, okay? Whereas before, of course, if we use flat map and map, we have, for each of those invocations, we have a new closure, which is overhead and can also have indirect overhead through boxing. Let's just passing values to closures can get you some overhead. So this can even be more efficient. But okay, let's see what are the limits of this existing async await in Scala, right? And so let's make our task a bit more complex, where we say, well, instead of converting just a single string, let's consume a stream of multiple strings, right? So we have kind of a publisher that emits multiple strings, and we have to convert all of them. And so the output of our solution should actually be a publisher that emits a stream of results. All right, so how do we do this? Well, let's first talk about streams, right? And so there's an effort called Reactive Streams, which I think is interesting, which builds on essentially earlier work on what is called Reactive Extensions, right? And so this kind of model, I'm just going to give you a quick overview. This is actually also in the JDK now, right? So it's basically essentially a small set of interfaces that have a protocol specified for how they have to be implemented, right? And so, of course, this is builds on prior work. So, you know, if you go back, you can go back all the way to a gang of 4 pattern here. The observer design pattern was kind of is an early ancestor, I would say. But the key prior work is actually the reactive extensions that Eric Meyer did originally for .NET, right? Where basically he clarified the relationship between observables and iterables, right? And you know, came up with a way to compose observables using higher order functions, right? So really kind of a functional way of composing things, but actually originally in like an OO language, like C#. And now the thing is, reactive streams now essentially takes reactive extensions, more or less, and says, well, let's add something to it that is somewhat missing, which is back pressure control. And so what this means is that essentially if I'm a subscriber, I'm going to subscribe to publishers, I need some way of making sure the publishers don't like overwhelm the consumers, right, the subscribers. So the subscribers should have a way to control the flow of events that they receive, right? And so I'm just going to give you a quick rundown of all these interfaces. And so the first one is publisher of T, and I'm using Java syntax now because this is how they are defined in the JDK since version 9, right? And so publisher of T emits events of type T, right, and they're received by subscribers. And so this interface has exactly one method, subscribe, where that is supposed to be called only by subscribers, and they can pass themselves as an argument, so that now the publisher can emit events to those subscribers. And the subscriber interface now has methods for each kind of event that the publisher can emit. And so compared to reactive extensions, there's actually one more event here, which is the first event that's going to be emitted. It's called onSubscribe, where if a subscriber is like successfully subscribes to a publisher, this onSubscribe method is called, and it receives a subscription object that is now passed on to the subscriber, right? So that the subscriber can use the subscription object to control the flow of events coming from the publisher, right? We'll see that on the next slide. But otherwise, we have sort of three methods for the three kinds of events that a publisher can emit. On next, that's the next event of type T. On error is an erroneous event. So the publisher, that's when the publisher terminates with an error. And so then the runtime system needs to pass down an exception to the subscriber. And then the final event is onComplete, where basically that says the publisher has terminated successfully, right? All right, and then so I mean that's fairly standard kind of things. The one thing that's maybe more surprising is the subscription interface, and that's what's used by subscribers, right? And they basically say, well, when I'm subscribed to a publisher, the publisher cannot send me anything until the subscriber has called request, specifying how many events the subscriber is ready to receive, right? And so that's the back pressure control, right? So that the subscriber can prepare their buffer, let's say, event buffer for incoming events, and tell the publisher, okay, this is how many events I'm ready to receive. And of course, we can also cancel subscriptions. All right, so far so good. And now if you take these things, usually we would not actually build, entire applications and systems just using those interfaces, right? The way it works is that, people build, large libraries that build on these basic interfaces, but that provide lots of ways to, build publishers and also compose them using higher order functions, just like with reactive extensions, right? So it's not uncommon to have like hundreds of methods to, compose publishers in different ways and build up pipelines. And of course, this has been implemented for many languages. Just to give you one example, by the way, who of you has seen reactive extensions before? Okay, some people, so it's good that I can actually show an example here. So this is taken from a very nice overview article from Eric Meyer called Your Mouse is a Database. So I really recommend you to look at that. There's no paywall behind it. It's not behind a paywall. So what this example does is it starts with an input field, a text input field, like a GUI called input, where the user can input text, right? And the text changes function creates a publisher that emits an event whenever the text in the input field changes, right? So for each time the contents of the input field changes, we have a new event. And this publisher, on this publisher, we call the select method. The select method essentially transforms the publisher into a new publisher where for each event of the text changes publisher, we emit an event which are all the completions for that word. Right, so imagine you have a text input field of a search engine, right? If you type in one word, typically a search engine would come up with suggestions for additional words you want to include in your query, right? So that's the scenario. And so for each published event word, our new publisher created by select will publish all the completions. And in this case, the completions are a publisher themselves. So that means the result of select, by the way, here's a picture. The result of select will be a new publisher, will be a publisher of string. Okay, so it will be a publisher that emits completions, right? And now, because we have too many publishers here, we should switch between them, okay? And the switch combinator basically says, okay, the switch combinator or method is called on a publisher of publishers, and in this case returns a simple publisher of strings. And the way it does it is it says, well, the first event that's received is a publisher of strings, the completions for the very first word. And so switch creates a publisher that will publish those events, so these are the red ones. And as soon as a new event is received, which is the completions for the next word, so for the changed word in the input field, then switch will switch to the completions, which is publisher, to the completions of the changed word and emit those, right? And so on and so forth. And of course, on that publisher, we can then subscribe, so that we can receive all of those events. So, as you can see, like with just a couple of methods, we can create quite intricate things. And this is actually one of the challenges with this style of programming, is that typically we have to explain the semantics using diagrams in some form. And so, in fact, if you look at the documentation for reactive extensions, they use what they call marble diagrams to explain the semantics of these different combinators, right? And so that's a challenge. The other challenge we have is actually just creating combinators. So a combinator like, let's say, select or switch or zip even, right? Creating those is actually not that simple. And particularly if these combinators are stateful, like a windowing combinator or, filters, stateful filters, I don't know. And finally, of course, what we're doing is we program in a style that is uses inversion of control, where basically we're constructing a computation, and then we leave it up to the runtime system to execute it, right? To schedule the computation according to the events that run. So it's quite different from running a sequential program on, let's say, the current thread of execution, right? It's a very different way of programming. All right, so now let's go back to our initial task, right? Our task was to convert a stream of multiple date strings and to consume them and to produce a publisher that produces a stream of results. Right, and we want to do this in direct style, and so using a model like async await that I've showed before. However, we run into some issues if we try to do that. The problem is that, first of all, await that we use to wait for the next event, well, it only takes futures as arguments, but we need to actually be able to await different stream events, like next event, error, or done. And also, async just creates a future that's completed once, but we need to actually create a producer that yields several events, right? So we can't use async await. And so the question is, can we extend the model somehow so that we can do these things? And this is what this project scala-async-flow is about. So the idea is that we extend the async await model so that we have first a variant of async that can create publishers instead of just futures, right? We call it rasync for now. And we need to generalize await from futures to stream events, like I mentioned. And we need to be able to also emit the different kinds of events. So we have variants of yield to yield different events. And once we well, let's first talk about generalizing await, right? So previously we had await that took future and future of t and returns a t. But now we need to await events that are produced by different asynchronous objects. So it could be futures, right? But it could also be publishers and maybe other async objects. And so the idea is that we have a notion of an asynchronous object that provides methods to receive or to await for the next events that they emit, right? And so the first method here is called getCompleted, which checks if there is if the asynchronous object has been completed with the next event. Completed is maybe not the best name actually in retrospect, but we can rename this, right? But basically saying, is there a next event ready to be consumed? And now this could be true or false. I mean, if there's no event, we just return null in our case, but we could have made this an option, obviously. The other thing is we could have a failure as well. So the asynchronous object that we await for could have failed. And so that's why we return a try here. And try in Scala is essentially a simple ADT that can be a success or a failure, right? And in case of failure, it contains the exception that the async object failed with. All right, so we need a way to check that. And then the second method we need is essentially a way to register an event handler that should run once the async object is completed with a try of t, right? So either a failure or the successful next event of type t, right? And you can ignore this part for now, okay? I will talk more about this later, but for now just ignore that. And if you're totally confused because you've used Scala before, this is actually Scala 3 syntax, so we'll talk about this later. But the key is that we can we need a very minimal interface actually for the async objects to make all of this work, okay? And okay, so once we've done this, we can actually now formulate our solution in quite a nice way. So what we can do is we use rasync to create a publisher of string, and now within this block of code, this is again a suspendable computation. So it means we can wait for the next events of streams, right? So we can say await date stream, and that returns an option which is empty in case the stream has terminated, or it's a non-empty option which has the next regular event on that stream. And by the way, if the stream has terminated with an exception, then await would throw that exception, and we can catch it just like with try catch, right? And fine. And so now what we can do is we can actually this is our first event that we've received if it's non-empty, and then we can just like match on it as before, and we again wait for, in this case, a future, right? So name of month that is not a stream, right? And so that's actually kind of important because we need to be able to wait for the events of different kinds of async objects, right? We don't want to fix, the parameter type of await to now just be publishers. No, it needs to be, we want to be able to also await futures, right? And once we've awaited the result of that future, we can yield our next event. Right? And so now this is inside a while loop, so we can publish many events on this stream. And finally, we can call yield done to say, well, now our stream is has terminated successfully. All right, so that's essentially a very direct way of kind of generalizing our earlier solution from futures to streams. Now, I want to talk a little bit about how to implement this, right? Because it's not entirely obvious how to implement suspendable computations, right? At least not in sort of mainstream languages, right? And so there are different alternatives. First is, of course, we could extend scala-async, right? Which is this macro for current Scala. We could do that and make it available for current Scala programs. We could also directly build it into the compiler. And we could say, okay, Scala version 3.1 should have it built in, right? And the third variant is to say, well, we can also build on top of a runtime environment that provides, for example, delimited continuations or fibers, right? And we've actually looked at 1 and 3, so I'm going to talk about those two a little bit. But first, let me talk about the API, which is also a very interesting point in terms of language design, right? Because basically, we have this R-async method, which takes a body, which normally is just a closure that evaluates to a value of type t, right? So arrow t, would be sort of what we would expect as the type of the closure. And the result, of course, is a publisher of t. Now, the thing is, we need essentially a context to be able to emit events. Okay, so if we call, let me go back here. If you call yield next here, well, we need to know, what is the publisher that should yield that event, right? So it's of course the enclosing, it's the publisher created by the enclosing R-async, right? And so we need to communicate that somehow to the yield next method, right? And turns out we can use a contextual abstraction to do that, and this is what given flow of t is all about. And this is actually called an implicit function type. Okay. Why is it called like that? Well, because flow of t here is the parameter type, but it's an implicit parameter. An implicit parameter is not, we don't pass an explicit argument to it when we call the function. No, it's provided implicitly. And there's actually a POPL paper from 2018 that talks about the foundations for those. But let me give you a quick overview here. So if you look at the signature, that's from before. And here's concrete usage, right, where we say R-async of int. We have a few expressions here. Say one of them is yield next 5, right? And okay, the final one is 3. Okay, so the final event that the stream emits is the integer 3. And now, because of this implicit function type, turns out the type checker will expand this piece of code into the following, where essentially the closure here is replaced with a closure that has this implicit parameter of type flow of int, right? And I call it $f to say it's a compiler-generated name, right? And now what's amazing here is that now that we have this parameter in scope, it means it's in scope throughout the whole block here, and so we can actually pass it to yield next, okay? Because it turns out yield next also has an implicit parameter, right? And so we can fill in this this flow of int that's available in the lexical scope, right? And so we know that, okay, this event is actually yielded on that flow object, right? And so if you look at yield next, we see that, well, it takes not only the event to be published, but it also has this implicit parameter, right, of type flow of t. And this implicit parameter is, of course, crucial because that's the thing that ultimately, yields the event, right? Turns out the publisher that's created by RAsync is actually contained in flow or provided by this flow object. Okay, so contextual abstraction is really powerful for this kind of programming model. And now, if we go back to RAsync, we can now create a new flow object, flow instance. And actually, in the current implementation, flow of T is actually a subclass of publisher of T. So we can actually return this object as the final result of RAsync, right? But what we do here is actually we introduce a so-called delegate for this type, and that's all it does is it introduces this flow object in the lexical context as the implicit argument that should be passed to all the places where we need an implicit parameter, right? So this thing will be passed automatically, you know, into, well, it will actually be passed to body, right? Because that's a function that takes this implicit parameter, right? And body itself will then pass it on to all the yield next calls and so on. All right, the other parts of the API are kind of similar in the sense that these functions await yield next, well, they each have, you know, they take this flow as an implicit parameter. Await takes, in addition, an execution context, but I don't want to talk about it. It's more for scheduling closures for execution, right, essentially. All right, so let's go back to the actual compilation, right? So the first option we had was using macros, and I don't want to spend too much time, probably, but this is sort of the minimal example you can think of where we have a publisher we await a single event from that publisher, and that of course returns an option because the publisher may have terminated, but in this case we assume we have at least one event and we get it out of the future, and that's this single event that we're publishing. Extremely simple example, but still we have a suspendable point here. Await may suspend, right? And so that means we have to compile this in some way. And the macro-based translation essentially consists of creating a state machine where this is just a class that has a method apply, and apply essentially runs the code of the RAsync body from different points in the source code, like either from the very beginning, right, from the very top, which is the case when the state is 0, right? We run from the very beginning. At the very beginning, we assign none to x, so that's the initialization that we do here. We assign none to x, right? And so that's in state 0. But then the next thing we do is we call await. And so here we get the corresponding subscriber and check if we already have an event to be consumed, right? So we can call get completed to check that. If the result is null, it means no, we have to suspend actually. And so what we do is we say, well, let's change our state to 2. That's the state where we want to resume later on when there is an event. So we want to be resumed in state 2. But we need to register an event handler that is invoked as soon as there's an event, right? So we call onComplete on our subscription or subscriber, and when the next event is there, it'll call apply again. Of course, this time in state 2. So that means when we have the completion, we will go to state 2, here we just check whether the event, you know, is a failure, in which case we need to fail ourselves, so our own result will be a failure. Right? Or we can continue in the happy path where we have an actual result, we assign it to x, and we go to state 1. And state 1 is everything that we do after the await, right? And so state 1 says, well, what do you have to do after the await? Assuming we have a result already assigned to x, this is what we already did, well, we just have to essentially evaluate the final expression, which is just x.get in this case, and put it into the result. Right, so this is essentially how this kind of state machine looks like. But I also want to mention this alternative, right, where we have a more powerful execution environment. In this case, Project Loom from OpenJDK. which actually provides delimited continuations, and fibers, which are very lightweight user mode threads. And this is actually a project under very active development, and there's actually a talk today by Ron Pressler at 4:15. So if you're interested, make sure to go to that one. So the idea is that essentially we can turn a task into a suspendable computation. So the idea is a task, which is a runnable here, has a body, and within the body we can suspend the execution at different points, right? And this is exactly what we need to do. So let's see how we can do it. So this is just to give you the hello world of continuations, right? It's basically saying, well, let's create a continuation, and when we call run on it, it'll start running it, and since continue is initially false, we will suspend, okay? And at this point we yield the continuation, so we will interrupt the execution, and that means run will actually return, and done is false, and so we go here, set continue to true, call it again, and when we call run again, we will actually continue from this yield point, right? And so we will resume, etc. So we can of course use this for our async. We will just say, well, let's make a continuation so that within body we can suspend and resume, right? And so that's actually a very simple way to do these things. I'm going to skip over a couple of things. One thing I want to point out is that actually there's a whole formalization of this programming model, okay? And what's interesting is we also have proof that well-typed programs actually satisfy satisfy the protocol for streams. Like for example, a publisher will never emit an event after done, let's say, right? So that's also on my homepage, so I encourage you to have a look at that. There's a couple more issues where we have some initial ideas, but I have to, I think, skip over that. One thing I do want to point out though, which is an open issue, which is the blue and red functions problem, where basically calling a suspendable method requires the caller to be suspendable as well. And so this kind of property propagates throughout the program. So for each higher order function, we need two versions, one that can call suspendable function, one that can't. So that's kind of a tricky issue. But yeah, let me conclude here, and thanks for your attention.
I think we have time for probably one question while we change speakers. So the next presenters, if you guys could come up and swap out the laptops, we can answer a question in the meantime, if anybody has any questions. No? Yes? Okay.
So, hello. So I had a question about Reactive Extensions. I saw there's a cancel method. I was wondering why is that needed actually? Why not just use unsubscribe? Or
why is cancel needed? Well, I think if you're a subscriber, right? If you subscribe to a publisher, to one or more publishers, it's just if you no longer want to receive events, then you call cancel in a subscription, right? Because otherwise you need to, you're bombarded with events that you don't want to receive.
Thanks.
All right. Then, yeah, thank you very much.